Today, we're diving deep into the paper SVD-Quant, Absorbing Outliers by Low-Rank Components for 4-Bit Diffusion Models. This paper tackles the challenge of deploying large diffusion models efficiently by employing aggressive 4-bit quantization. Let's start with the core problem. Why is 4-bit quantization so challenging for diffusion models, and why are existing methods insufficient?
The primary hurdle with 4-bit quantization is the extreme sensitivity to outliers in both weights and activations. Conventional post-training quantization, PTQ techniques like smoothing, which redistribute outliers, prove inadequate at this aggressive bit depth. Both weights and activations become highly vulnerable, leading to significant quality degradation. The paper argues that simply redistributing outliers isn't enough. They need to be absorbed.
SVD-Quant proposes a novel solution. Can you outline the key components of the SVD-Quant approach?
SVD-Quant introduces a low-rank branch to absorb these outliers. It's a two-step process. First, it uses smoothing to consolidate outliers, shifting them primarily to the weights. This makes the activations easier to quantize. Then, it employs Singular Value Decomposition, SVD, on the modified weights to separate them into a high-precision, low-rank component and a low-magnitude residual. The residual, now significantly less prone to outliers, is then quantized to 4 bits.
That's an interesting approach. Why is SVD particularly well suited for this task?
SVD is ideal because it allows us to capture the most significant information in the weight matrix with a low-rank approximation. The dominant singular values, often associated with outliers, are moved to the high-precision, low-rank branch, leaving the residual with a much smaller magnitude and fewer outliers, making it easier to quantize accurately. The Eckart-Younger-Mirsky theorem supports this approach.
However, adding a separate low-rank branch could introduce significant overhead, negating the benefits of quantization. How does the paper address this?
The paper cleverly addresses this with a co-designed inference engine called Nunchuku. Nunchuku fuses the kernels of the low-rank branch with those of the 4-bit branch. This kernel fusion minimizes redundant memory access, eliminating the extra data movement that would otherwise slow down inference. It also seamlessly supports off-the-shelf low-rank adapters, LoRa's, without requiring re-quantization.
The paper mentions both INT4 and FP4 quantization. What are the trade-offs between these two approaches?
INT4 offers potential for higher speedups on hardware that supports it efficiently, but FP4 might offer better precision in some cases. The choice depends on the specific hardware and the desired balance between speed and accuracy. The paper demonstrates results for both.
What are the key results and performance improvements reported in the paper?
The paper demonstrates significant improvements across several large diffusion models, including Flux.1, PixArt-Σ, and SDXL. On the 12B parameter Flux.1 model, SVD-Quant achieves a 3.5x memory reduction compared to the BF16 baseline and a 3.0x speedup over a 4-bit weight-only quantized baseline on a 16GB RTX 4090 laptop GPU. The speedup is even more dramatic on the laptop due to the elimination of CPU offloading. The results also show that SVD-Quant maintains or even improves image quality compared to other 4-bit and 8-bit quantization methods.
The paper highlights the seamless integration with LoRa's. How significant is this feature?
This is a crucial aspect. Many existing quantization methods require refactoring and re-quantization when using LoRa's, adding complexity and potentially degrading performance. Nunchuku's kernel fusion allows for straightforward integration, making SVD-Quant more flexible and practical for real-world applications.
The ablation study provides valuable insights. What were the key findings from that analysis?
The ablation study clearly demonstrates the superiority of the combined SVD and smoothing approach. Using SVD alone, or naive quantization, resulted in poor image quality. Smoothing alone offered some improvement, but was still significantly inferior to the combined method. The study also showed that existing low-rank compensation methods, like LoRC, were not as effective as SVD-Quant's approach of decomposing the weights and quantizing only the residual.
What are the limitations of the current work, and what are potential avenues for future research?
A key limitation is the lack of results on Blackwell GPUs, which natively support FP4 and microscaling. Future work could explore this hardware to potentially achieve even greater speedups. Further research could also investigate optimal rank selection strategies and explore the application of SVD-Quant to other model architectures and tasks beyond text to image generation. Adapting the method for quantization-aware training is another promising direction.
The paper mentions the open sourcing of the quantization library and inference engine. How accessible are these tools to the community?
Both the quantization library and the Nunchuku inference engine are publicly available, making SVD-Quant readily accessible for researchers and practitioners to experiment with and integrate into their workflows. This open source nature fosters collaboration and accelerates progress in the field.
Considering the results and the open source availability, how impactful do you believe this work will be on the deployment of large diffusion models?
I believe this work is highly impactful. The significant memory reduction and speedup achieved by SVD-Quant, combined with the seamless LoRA integration and open source availability, significantly lower the barrier to deploying large diffusion models on resource-constrained devices. This opens up exciting possibilities for interactive AI applications on PCs and mobile devices, making advanced image generation more accessible to a wider audience.
The paper mentions the use of different metrics for evaluating image quality. Can you elaborate on the choice of these metrics and their relative importance?
The paper uses a comprehensive suite of metrics to provide a holistic evaluation of image quality and similarity to the original 16-bit models. FID and LPIPS capture perceptual similarity, while PSNR provides a numerical measure. Image Reward offers an approximation of human preference, and CLIP IQA and CLIP Score assess image quality and text-image alignment using CLIP. The combination of these metrics provides a more robust and nuanced assessment than relying on a single metric. Finally, what is the most significant takeaway from this research for practitioners working with diffusion models?
The most significant takeaway is that SVD-Quant offers a practical and effective way to achieve significant speedups and memory savings in large diffusion models without sacrificing image quality. The combination of the novel quantization technique and the efficient inference engine makes it a compelling solution for deploying these models on resource-constrained platforms. The open source nature of the tools further enhances its accessibility and potential impact.
Thank you for this insightful discussion.